Next, introduction. A team of sciences AI students conducted a study in Morocco published on Kaggle to examine how lifestyle factors like caffeine, alcohol, and exercise affect sleep patterns and quality. Data was collected using surveys, actigraphy, polysomnography, then analyzed how to identify ways to improve sleep.
Assalamualaikum. My name is Nur Fakira Akila binti Ahirushi, and I will present about basic mathematical model, which is linear model. So, as we know, the equation for linear model is y equal to a plus bx. Therefore, from the 20 data that we have, we substitute the value of x and y into the linear equation. After that, we can set up the matrix for M with the dimension 20 by 2 and y with the dimension 20 by 1. After that, we can form the value for the normal system. We use the least square solution to find V by multiplying the inverse of M transpose M and M transpose Y. Therefore, we get the best fit linear curve as is shown. Next, to find the error vector, the formula of the error vector is matrix Y minus matrix MV. Therefore, we also can find the magnitude of error vector, which is we get 2.3396. So, is the graph of best fit curve for linear model and also the graph of error vector for linear model.
Today, I'll be explaining the cubic method and why we use it. This method is helpful and we suspect a nonlinear relationship between the variables that can be best described by a cubic equation y equals to ax cubic plus bx squared plus cx plus d. On the left, we see our input data matrix M for the independent variables and their powers. Vector y representing the dependent variable. We use the normal equation M transpose M times x equals to M transpose y to set up the problem. Then the least square method minimizes errors to find the coefficient A, B, C, and D. This ensures the cubic model fits data as accurately as possible. The result shown at the bottom right gives us the final equation for the modeling the relationship. Now let's evaluate the accuracy of our cubic model. To do this, we calculate the error vector represented as E equals to y minus mv. This gives us the difference between the actual y values and the predicted values from the model. Next, we find the norm of the error vector denoted as E, which measures the overall error in the model. In this case, the norm is 2.0465, indicating a relatively small error, meaning our model fits the data well. Finally, combining all the coefficients from the previous slide, we arrive at the best fit cubic curve y equals to 16.8324 minus 0.733 2x plus 0.01769x squared minus 0.00013x cubed. This equation captures the underlying pattern in the data while minimizing error. To conclude, let's visualize the result of the cubic model. On the left, we have the cubic model graph showing the curve represented by our equation. The blue curve fits the data point and captures the nonlinear pattern effectively. You can see how the curve adjusts for the turning point in the data, confirming the model's flexibility and accuracy. On the right, we have the residual plot which shows the error value for each data point. The residuals are mostly scattered around zero without a clear pattern, indicating that the cubic model is appropriate for the data and does not leave systematic errors. Together, these graphs validate the model as a good fit for the data.
Last but not least, I will present about the conclusion and analysis of this project. Based on the three models above, the following error magnitudes in the approximation are obtained. We get three error magnitudes for the types of best fit curve, which is linear, quadratic, and cubic. The error magnitude for linear is 2.3396 and the error magnitude for quadratic is 3.4882 And last, the area magnitude for qubit is 2.0465. The best fit curve in this case, which will give the best approximation, is qubit model because it has minimum error term of this magnitude.